Your jaw generates more force per square centimeter than any other voluntary muscle system in your body. The masseter muscle, the muscle you can feel tighten when you clench your teeth, produces a bite force of up to 70 kilograms, roughly 700 newtons, concentrated on a molar surface area of approximately 1 square centimeter. You've been using that force 3 times a day, every day, for your entire life. And the number of times you apply it to each mouthful of food changes your blood sugar, your satiety hormones, the preparedness of your stomach, the blood flow to your brain, and the rate at which your digestive system extracts nutrients from the meal you just ate. Variable is not what you eat. It is how many times your jaw closes before you swallow. There is a surface area calculation that governs how efficiently your digestive enzymes can access the food you send them, and the calculation depends entirely on particle size. There is an enzyme that only works in your mouth, that is destroyed the moment food reaches your stomach, and whose window of activity is determined by how long you chew. And there is a venous pump built into the muscles of your jaw that drives blood through your brain with every chewing cycle. A pump that most people operate at 1/3 of its capacity because they swallow too soon. All of it comes later. Start with the physics of what happens to food when you chew it, because digestion is an engineering problem, and the engineering begins in your mouth. Stomach and small intestine are chemical reactors. They break food down through enzymatic hydrolysis, enzymes attacking molecular bonds and reducing complex molecules to absorbable components. But an enzyme can only act on the surface of a food particle. It cannot reach the interior until the surface has been digested away layer by layer, the way erosion works on a rock. The rate-limiting factor in digestion is therefore surface area to volume ratio, the total surface area available for enzymatic attack relative to the total volume of food that needs to be processed. Surface area to volume ratio is governed by particle size. A large particle has a low ratio. Most of its volume is hidden in the interior, inaccessible to enzymes. A small particle has a high ratio. More of its volume is exposed at the surface. The relationship is not linear. Reducing a particle's radius by half doubles the surface area to volume ratio. Reducing it by a factor of 10 increases the ratio tenfold. The physics of fragmentation means that the difference between a food bolus chewed 10 times and a food bolus chewed 30 to 40 times is not a modest improvement in digestive efficiency. It is a change measured in orders of magnitude. Food chewed 40 times produced particles with a median diameter of approximately 2 millimeters, compared to approximately 4 to 6 millimeters after 15 chews. Jalabert, Malbus, and colleagues published this in Food Quality and Preference. The surface area available for amylase, pepsin, and lipase activity roughly tripled. Food was identical in both conditions. Chemical reactor was identical. The variable was the mechanical pre-processing your jaw performed before swallowing, and that variable tripled the surface area the digestive system had to work with. Consider what that means for the meal you ate most recently. The food that arrived in your stomach was a collection of particles at a specific size distribution, determined entirely by how many times you chewed before swallowing. If you chewed each bite 10 to 15 times, which is typical for adults eating at a normal pace, the particles were 4 to 6 millimeters in diameter, with relatively low surface area available for enzymatic attack. Your stomach and intestines had to work through those particles layer by layer, from the outside in, dissolving the surface before reaching the interior. If you had chewed each bite 30 to 40 times, the particles would have been 2 millimeters or smaller, with 3 times the surface area exposed. Your digestive system would have completed the extraction in less time with less effort, recovering more of the available nutrients. The difference was not in the food. It was in the state the food was in when your jaw released it. Well, and the particle size is only the first computation your jaw performs. Because there is an enzyme in your mouth that cannot work anywhere else in your body, and the number of chewing cycles determines how much of your food it reaches. Salivary amylase is secreted by the parotid, submandibular, and sublingual glands during mastication. The act of chewing triggers its release. Its function is to begin breaking down starch into shorter glucose chains before the food leaves your mouth. Its activity is pH dependent, optimal at the near neutral pH of saliva, approximately 6.8 to 7. Moment food reaches your stomach, the pH drops to 1.5 to 3.5. Hydrochloric acid denatures the amylase, unfolding its protein structure, destroying its enzymatic function permanently. Salivary amylase is dead on arrival in the stomach. The destruction is not gradual. It is immediate. The acid environment unfolds the enzyme's three-dimensional structure within seconds, and the unfolded protein cannot refold. The enzymatic capacity is gone. This means every molecule of starch that salivary amylase will ever process in your body must be processed in your mouth. There is no second chance. The pancreas produces its own amylase in the duodenum, but pancreatic amylase works on a different timeline and produces a different glucose absorption profile. Salivary amylase predigestion, the partial breakdown that occurs during chewing, is a unique enzymatic event with a unique downstream consequence, and its duration is controlled entirely by how long you chew. Window for salivary amylase to act on the starch in your food is exclusively the time that food spends in your mouth. 5 chews provide roughly 5 to 8 seconds of oral exposure. 30 chews provide 30 to 45 seconds. The starch digestion that occurs in your mouth, and can only occur in your mouth, is directly proportional to how long you chew. Think about what that means for the bread you ate at lunch, the potato you had at dinner, the rice you will eat tomorrow. The starch in each of those foods has a window of enzymatic access that opens when the food enters your mouth and closes permanently when it reaches your stomach. 5 chews give salivary amylase 8 seconds to work. 30 to 40 chews give it 30 to 45 seconds. The difference in starch predigestion between those two scenarios is not subtle. It changes the downstream chemistry of everything that follows. Now, the downstream chemistry. Because starch that arrives in your stomach partially predigested by salivary amylase is processed differently from intact starch granules, and the difference is measurable in your blood. Intact starch, starch that was swallowed with minimal salivary amylase exposure, arrives in the duodenum as large, unprocessed granules. Pancreatic amylase must break them down from scratch, producing a rapid release of glucose into the bloodstream. A sharp spike in blood sugar, followed by a correspondingly sharp insulin response. Predigested starch that spent 30 to 45 seconds exposed to salivary amylase in your mouth, arrives in the duodenum partially broken down. The glucose release is more gradual. The blood sugar curve is flatter. The insulin response is more measured. The glycemic index of a food, the number that ranks how quickly it raises blood sugar, is not a fixed property of the food. It is partly a property of how long you chewed it. The mechanism predicts measurably different blood sugar curves from the same food chewed 10 times versus 30 to 40 times, more amylase predigestion producing more gradual glucose release, and preliminary data supports the prediction. The variable that changes the curve is not the bread. It is the number of chewing cycles your jaw performed before swallowing. For the person over 65 managing blood sugar, whether through diabetes, prediabetes, or the gradual insulin resistance that aging produces in nearly every adult, this is not a theoretical distinction. The glycemic response to every starchy meal they eat is being partly determined by a mechanical variable that no dietary advice typically mentions. The food is identical. The portion is identical. The blood sugar response changes with the number of times the jaw closes. A person who has been told to reduce their glycemic load, to eat fewer carbohydrates, to choose low glycemic foods, to monitor their blood sugar after meals, has never been told that the mechanism predicts identical food producing a lower glycemic response when chewed more thoroughly, and the preliminary data supports it. The jaw is part of the blood sugar equation, and it is the part the person can change at the next meal without changing anything else. You see, and your jaw is not only processing food mechanically and enzymatically, it is also programming your gut to receive what is coming. Because the vagus nerve is listening to every chewing cycle, and it is using that information to prepare your stomach before the first bite arrives. Mastication triggers a cascade of preparatory signals to your digestive tract before any food has been swallowed. This is the cephalic phase of digestion, the anticipatory response your body initiates based on sensory input from your mouth. Chewing stimulates the vagus nerve through mechanoreceptor activation in the periodontal ligaments, the connective tissue suspending each tooth in its socket, and in the temporomandibular joint capsule. Vagal signal reaches the dorsal motor nucleus of the vagus in the medulla, which initiates gastric acid secretion, pancreatic enzyme release, gallbladder contraction, and increased intestinal motility. All of this happens before the first bolus reaches your stomach. Prolonged chewing amplifies the cephalic phase signal. Your gut receives a stronger preparatory instruction from 30 to 40 chews than from 10. A stomach that has been preparing for 30 to 45 seconds of chewing phase vagal stimulation has higher acid concentration, more pepsinogen activated to pepsin, and stronger peristaltic contractions than a stomach that received 5 to 8 seconds of signal. The food arrives into a more prepared chemical environment. Enzymatic breakdown begins faster. Transit efficiency increases. Nutrient absorption in the small intestine is more complete. If you have ever experienced the sensation of food sitting heavily in your stomach after eating quickly, the sense that digestion has stalled, that the food is just occupying space rather than being processed, you may have been experiencing a stomach that was not prepared for what it received. Cephalic phase signal was too brief. Acid secretion was insufficient. Pepsinogen activation was incomplete. The food arrived into a chemical environment that was still ramping up rather than one that was ready. The heaviness is not imagined. It is the physical consequence of a chemical reactor operating below its design preparation level because the jaw did not provide enough advance warning through the vagus nerve. Jaw is not just breaking food into smaller pieces. It is sending a preview to your gut through the vagus nerve at every chewing cycle, telling the stomach how much food is coming, how long to expect, and how aggressively to prepare. Fewer chewing cycles mean a weaker preview. The gut is less prepared. The food arrives into a stomach that was not expecting it yet. Now, the satiety system. Because there's a clock running from the moment you start eating, and the number of times you chew determines whether your body's fullness signal arrives before or after you have already eaten too much. Satiety signaling operates on a delay. Cholecystokinin, released from eye cells in your duodenal wall in response to fat and protein arriving from the stomach, takes approximately 15 to 20 minutes from the start of eating to reach concentrations that your hypothalamus registers as fullness. Peptide, YY, released from L cells in the ileum, takes 20 to 30 minutes. Leptin, released from adipose tissue in response to insulin, operates on an even longer delay. Your hypothalamic satiety center integrates these signals and produces the conscious sensation you recognize as being full. Clock runs at one speed regardless of how fast you eat. The question is, how much food enters your stomach before the clock runs out? Increasing chewing cycles per bite from 15 to 40 reduce total caloric intake at a meal by approximately 12%. Lee and colleagues published this in the American Journal of Clinical Nutrition. Mechanism is not appetite suppression. It is temporal alignment. More chewing cycles slow the eating rate, allowing the satiety hormones to reach effective concentrations before the meal is over complete. 30 to 40 chews per bite is a mechanical pacing system that synchronizes your food intake with the hormonal feedback loop that controls it. If you have ever finished a meal and felt uncomfortably full 20 minutes later, the specific discomfort of having eaten too much that arrives well after the plate is empty, you were experiencing the satiety signal arriving after the eating had stopped. Your gut had finally produced enough cholecystokinin and peptide YY to tell your hypothalamus to stop eating. But the eating stopped 10 minutes earlier based on plate emptiness, not on satiety. The signal and the behavior were out of phase. Mismatch is mechanical, not behavioral. You are not eating too much because you lack willpower. You are eating too much because you are eating faster than the hormonal feedback system can respond. The satiety system was calibrated for a jaw that chewed 30 to 40 times per bite, producing a meal duration of 20 to 25 minutes, which is the window the hormones need to reach effective concentrations. Eating at 10 to 15 chews per bite compresses the meal to 8 to 12 minutes. The food is consumed before the signal arrives. Thorough chewing brings the timing into phase, not by changing the signal, but by slowing the eating to match the speed at which the signal travels. Particle size, enzyme exposure, gastric preparation, hormonal timing. 4 systems, each independently improved by the number of chewing cycles. There is a 5th, and then what the jaw does for the brain. Because there is a vascular pump built into the muscles of your jaw that drives blood through your cerebral circulation with every chewing cycle, and most people are running it at a fraction of its capacity. Pterygoid venous plexus, a network of veins surrounding the lateral and medial pterygoid muscles in your jaw, acts as a venous pump during chewing. Contraction and relaxation of the pterygoid muscles during each chewing cycle compresses and releases the plexus, pumping venous blood from the region and promoting arterial inflow to the middle meningeal and deep temporal arteries. Increased arterial inflow reaches your cerebral circulation via the middle cerebral artery territory. Functional MRI during gum chewing showed increased cerebral blood flow in the prefrontal cortex, the somatosensory cortex, and the hippocampus. Hasegawa and colleagues published this in the Journal of Dental Research. The study measured sustained rhythmic chewing on gum rather than normal meal mastication. The extrapolation to meals is reasonable, but the direct measurement was on gum. Prefrontal cortex is where your executive function operates: planning, decision-making, attentional control. Hippocampus is where memory consolidation occurs, the region most vulnerable to age-related atrophy. Your jaw, during every meal, is driving blood through the brain regions most associated with attention, sensory processing, and memory. The alertness that follows a thoroughly chewed meal, the sense of mental clarity that is often attributed to the nutrients themselves, is partly vascular. The pterygoid pump was operating throughout the meal, driving arterial blood through the cerebral circulation with every chewing cycle. A meal chewed quickly provides fewer pump cycles, less cerebral blood flow, and less of the post-meal alertness that thorough chewing produces. Think about the daily arithmetic. A person who eats 3 meals a day with 30 chewing cycles per bite performs approximately 3,000 to 4,500 chewing cycles per day. Each cycle activates the pterygoid venous pump, stimulates trigeminal nerve afferents that project to the reticular formation and contribute to cortical arousal, and drives blood through the cerebral circulation. A person who eats 3 identical meals with 10 chewing cycles per bite performs 1,000 to 1,500 cycles. The daily difference in cerebral blood flow stimulation, accumulated across 365 days, across decades, is the difference between a system that is regularly flushed and one that is not. Over a decade, the cumulative difference is millions of additional pump cycles, millions of additional trigeminal signals, a vascular and neurological input that one brain received and the other did not, 3 times a day, every day, for years. Relationship between mastication and cognitive function in older adults is epidemiologically consistent. Adults with fewer teeth, and therefore reduced masticatory function, had measurably higher rates of cognitive decline and dementia, as Ono and colleagues reviewed in the Journal of Oral Rehabilitation. Masticatory performance correlated with executive function scores in adults over 70. Wagenberg and colleagues published this in the same journal. The correlation is consistent and the vascular mechanism is plausible. The pterygoid pump exists, the blood flow increase during chewing is measurable, and the trigeminal afferent pathway to cortical arousal is established. Whether the chewing itself is the causal variable or a marker of broader health, people who lose teeth tend to have worse overall health and other risk factors, has not been isolated with the precision the other mechanisms in this script have been. The direction is clear. The causal specificity is still being established. Implication for the person over 65 is direct. Every tooth lost reduces the efficiency of the pterygoid pump. Fewer functional teeth means fewer effective chewing cycles, weaker muscle contraction, less venous compression, less arterial inflow. Dentures restore the ability to process food, but do not restore the periodontal mechanoreceptors that were lost with the teeth, the Ruffini endings and Merkel cells that provided the trigeminal afferent input contributing to cortical arousal. The tooth replacement solves the eating problem. It does not solve the brain stimulation problem. The person with dentures who chews soft food with minimal effort is receiving less cerebral blood flow stimulation per meal than they received when they had natural teeth chewing harder food, and the deficit accumulates across 3 meals a day, 365 days a year, for every year the teeth have been absent. That finding, cognitive decline correlating with masticatory function, through a vascular and neurological pathway that the jaw drives 3 times a day and that tooth loss progressively eliminates, reframes what tooth loss means. The jaw is not merely processing food, it is maintaining the brain. And the loss of teeth, which is treated as a dental problem, managed with dentures and implants that restore cosmetic function, is also a loss of the mechanical pump and the trigeminal afferent stimulation that the brain was receiving 3 times a day for decades. The dental problem is a neurological problem. The mouth is connected to the brain through a vascular pump that nobody discusses outside of dental research. Now, the mechanotransduction system. Because your jaw is not only pumping blood and signaling the vagus nerve, it is also reading the food and sending a detailed report to the brainstem before you swallow. Periodontal ligament, the connective tissue suspending each tooth in its socket, contains Ruffini endings and Merkel cells that encode bite force, food texture, and particle hardness with every chewing cycle. These mechanoreceptors provide your brain with real-time data about the physical properties of the food being chewed. Hard, soft, gritty, smooth, fibrous, homogeneous. Information is relayed to the nucleus tractus solitarius in the brainstem, which coordinates the digestive preparation signals sent to your stomach and pancreas. Your gut receives a preview of what is coming. Not just that food is being eaten, but what kind of food, based on its mechanical properties as reported by the teeth that are processing it. A fibrous vegetable and a soft piece of cheese produce different periodontal signals and different cephalic phase outputs. Your jaw is performing a material analysis of every bite, measuring resistance, texture, and fragmentation progress, and transmitting the results to your brainstem. How precisely the brainstem calibrates enzyme ratios and acid concentration for different food types based on this periodontal input is mechanistically plausible but not yet measured at the resolution of individual meals. What is established is that periodontal mechanoreceptors provide texture and hardness data to the nucleus tractus solitarius, and that cephalic phase output varies with the sensory input the mouth provides. 5 chews provide a sparse dataset. 30 to 40 chews provide a comprehensive one. The gut that receives a comprehensive preview prepares more accurately than the gut that receives a sparse one. Well, and 30 is not an arbitrary number, because the physics of fragmentation, the kinetics of salivary amylase, and the timing of satiety hormones converge at approximately one threshold. 30 to 40 chews per bite is the approximate range at which particle size reduction reaches the plateau of diminishing returns for most solid foods. Additional chewing cycles produce minimal further fragmentation because the particles have reached a size where they deform rather than fracture under bite force. It is the approximate threshold at which salivary amylase exposure becomes sufficient for meaningful starch pre-digestion, 30 to 45 seconds of oral exposure rather than 5 to 8. And it is the approximate eating speed that brings meal duration to 20 to 25 minutes. The window where satiety hormone signaling catches up with intake. 3 independent systems: mechanical fragmentation, enzymatic exposure, and hormonal timing, converging on one number of chewing cycles. Convergence is not designed. It is the result of a digestive system that evolved to receive food in a state of thorough mastication. Because for the majority of human evolutionary history, food required thorough mastication. raw plants, tough meats, unprocessed grains, and the downstream systems calibrated their timing to the input the jaw was providing. That convergence, three independent systems arriving at one mechanical threshold through completely different biological pathways, stopped me when I first encountered it in the digestive physiology literature. Because it means 30 to 40 chews is not a health tip, it is the operating specification. Your digestive system was engineered to receive food that has been mechanically processed to a specific particle size, enzymatically pre-treated for a specific duration, and delivered at a specific rate. The engineering was done by natural selection over millions of years of hominins eating food that required thorough mastication, and the downstream systems calibrated their timing, their enzyme concentrations, their hormonal delays, and their vascular pumping to the input the jaw was providing. Every system in the chain, amylase kinetics, gastric preparation, satiety timing, cerebral blood flow, was tuned to the output of a jaw chewing 30 to 40 times per bite. Modern eating, soft foods, minimal chewing, rapid consumption, delivers food that meets none of those specifications. The system still works. It works less efficiently, with higher glycemic spikes, less complete nutrient extraction, weaker cephalic phase preparation, delayed satiety signaling, and reduced cerebral blood flow stimulation. The system tolerates the mismatch. It was not designed for it. Consider your own meals: soft bread, cooked pasta, tender meat, processed foods engineered for ease of consumption. Most of what you eat requires 10 to 15 chews before your jaw releases it. Not because that is adequate, but because the food offers so little mechanical resistance that your jaw has nothing left to fracture. Your ancestors ate raw roots, fibrous plants, tough game meat, and unprocessed grains that demanded 40 to 50 chewing cycles per bite simply to reach a swallowable particle size. Their digestive systems receive food at the particle size, amylase exposure, and delivery rate they were calibrated for. Because the food itself enforced the calibration. Your food does not enforce it. The jaw is capable of 30 to 40 chews per bite. The food does not require it. The decision to chew thoroughly is a decision to manually provide the mechanical input that the food no longer demands, restoring the operating specifications that your digestive system was built to receive. Intervention requires no equipment, no prescription, and no change in diet. Food stays the same. The portions stay the same. Nothing about the meal changes except the number of times your jaw closes on each mouthful before you swallow. What you will notice if you try it at the next meal is that the food tastes different. 30 chewing cycles expose the food to your taste receptors for 3 to 4 times longer than 10 cycles. Flavors that you normally register only briefly. The sweetness of bread as amylase begins converting starch to maltose on your tongue. The bitterness of vegetables as cell walls rupture and release phytochemicals. The umami of meat as proteins begin to break down. Become more pronounced because the contact time between food and taste buds is extended. The meal becomes more flavorful without any change in ingredients. Your jaw is not only processing food for your gut and pumping blood for your brain, it is also determining how much of the food's flavor you actually experience. 10 chews gives you a preview. 30 gives you the full signal. You will also notice that the meal takes longer, 20 to 25 minutes instead of 8 to 12. The additional time is not wasted. It is the time your satiety hormones need to reach your hypothalamus, the time your salivary amylase needs to pre-digest the starch, the time your cephalic phase needs to fully prepare your stomach, and the time your pterygoid pump needs to drive blood through your cerebral circulation at full capacity. The meal is not slower. It is running at the speed the system was designed to operate. Your jaw is the strongest voluntary muscle system in your body. It generates 700 newtons of force, concentrated on a square centimeter thousands of times per day. And the number of times it closes on each mouthful of food changes the surface area available to your digestive enzymes, the duration of salivary amylase activity in the only environment where it can function, the timing of the satiety signal that tells your brain to stop eating, and the volume of blood pumped through your cerebral circulation during every meal. The jaw does the math. The gut depends on the answer.